We have learned how to draw Lewis structures, but sometimes it's possible to draw more than one Lewis structure that's legal according to the rules that we learned for drawing Lewis structures. So then you need a strategy to choose between alternative structures, and that strategy involves a tool called formal charge. So what formal charge basically is a difference between how many valence electrons are owned, so to speak, by the atom when it's just an atom, not part of a compound. So in other words, the normal number of valence electrons, and the electrons that it owns, so to speak, when it is in the compound, when it's in the bonded situation. So how you can calculate that is you think about the number of valence electrons in the unbonded atom. So that's like the normal number of valence electrons, like column 5s, like nitrogen, that's 5. Column 6s, like oxygen, that's going to be 6. And then you subtract from that 1 for each bond to the atom and 1 for each unshared electron. Not electron pair, but each unshared electron. Best way to learn how to do this is with some examples. So let's take water. So think about the hydrogen in water. It owns, as an unbonded atom, 1 electron. So we'll take that 1 and we'll subtract the number of bonds, which is 1, and the number of unshared electrons, which is none. So its formal charge is 0. Now this single bonded hydrogen is also going to have a formal charge of 0. So there are some patterns that you learn pretty quickly. Now let's tackle the oxygen. As an unbonded, remember oxygen's a column 6, so that has 6 electrons. And then here it's got 2 bonds, so we'll take away 2. And then it's also got 4 unshared electrons. 2 pairs is 4 unshared electrons. 6 minus 2 plus 4 is 0, so that means the formal charge on oxygen in water is also 0. Here's ammonia, NH3. We've already seen that a single bonded hydrogen is a 0, so we can just go with that. Now let's look at nitrogen. Nitrogen is a column 5, so normally in its unbonded state, it owns 5 electrons. We're going to take away from that the number of bonds, which is 3 in this case, plus the number of unshared electrons, which is 2. So that gives us a formal charge of 0 on the nitrogen. Now that we know how to find formal charge, how do we use it to pick a preferred structure? Well, the structure that has the lower overall formal charges is more likely. And it's important to note that this doesn't mean the lowest sum of formal charges. This means the one that has the fewest formal charges that aren't 0 is maybe a better way to say that. That's the one that turns out to be more likely. So here's an example. H2SO4, one way we could draw it would be like this. Let's pick out formal charges. We already see single bonded hydrogens here, and we know that those are going to be 0. So the hydrogens have a formal charge of 0. I'm going to also show you a kind of a shortcut. Here's what I do when I'm finding formal charge. I think about the normal number of valence electrons in the atom, and then I count backwards from there. So for this oxygen here, starting from 6, I'm going to count down 5, 4, 3, 2, 1, 0. So that means that the formal charge on that oxygen is a 0. Now here's an oxygen that's double bonded in exactly the same way, so that's going to also be a 0. This oxygen up here, starting from 6 and counting backwards, 5, 4, 3, 2, 1, 0, negative 1. So that means that the formal charge on that oxygen up at the top is going to be a negative 1. And then here's a single bonded oxygen down here. That count would go exactly the same, so we know that's also going to be a minus 1. The sulfur in the middle. Sulfur is a column 6. That means 6 valence electrons. So counting backwards from 6, 5, 4, 3, 2. So that means the formal charge on that sulfur is going to be a plus 2. Here's another version of H2SO4 that is legal to draw. Remember, sulfur can have an expanded octet, so it would be okay. Let's assign formal charges. We know that these H's are going to be 0. We know that double bonded O's, like the type that were in the other structure, are going to be 0s. So those two have a 0. Now let's tackle the oxygen at the top here. Starting from 6 and counting backwards, 5, 4, 3, 2, 1. That's also a 0. So that means the formal charge on this oxygen is a 0, And since this oxygen is identical in bonding, that's also going to be a 0. So since the structure on the right has all zeros for formal charges, and the one on the left has some formal charges that aren't zeros, the preferred structure would be that one. Sometimes it's sort of a tie. And in that case, the structures that have the negative formal charge on the most electronegative element are the ones that are the most likely. An example would be the thiocyanate ion. So thiocyanate, one way that you could draw it would be like this. Let's figure out the formal charges. For nitrogen, which is at column 5, counting backwards, 4, 3, 2, 1, 0. That would put a 0 formal charge there. For carbon, starting from 4 and counting down, 3, 2, 1, 0. That would be its formal charge. Sulfur is a 6, starting from 6 and counting down, 5, 4, 3, 2, 1, 0, negative 1. So that would put a formal charge of negative 1 on sulfur. Another way you could draw it would be like what we have here on the right. Let's do our formal charges. For nitrogen, starting from 5 and counting down, 4, 3, 2, 1, 0, negative 1. Carbon, starting from 4 and counting down, 3, 2, 1, 0. Same formal charges in the other structure. For sulfur, starting from 6, 5, 4, 3, 2, 1, 0. So the sulfur has a formal charge of 0. Because nitrogen is higher on the periodic table, closer to the upper left corner, it's the more electronegative of the two. So it's preferable to have the negative formal charge on nitrogen compared with sulfur, so that would be the preferred structure. Here are 3 possible structures for HNO3. Let's find the one that's preferred. First of all, we can eliminate the one on the right because nitrogen is making 5 bonds. That requires an expanded octet, and you can't do that for nitrogen because it's only in period 2. So that one's out. Now let's compare the other two. Assign formal charges. We already have seen from previous examples that a single bonded hydrogen, which is every hydrogen in a compound, that has a formal charge of 0. A single bonded oxygen, we've seen examples of that before, but let's just double check. Starting from 6 and counting down, 5, 4, 3, 2, 1, 0, negative 1. That's a minus 1. Here's a double bonded oxygen, starting from 6 and counting down, 5, 4, 3, 2, 1, 0. And then here's a double bonded oxygen. We've seen this before. That's also a 0. Now let's shift to the one on the left. Here's a single bonded O. We've already done that one. That's a negative 1. Nitrogen in this structure, starting from 5 and counting down, 4, 3, 2, 1. That's a plus 1. Plus 1. Oxygen, single bonded O, just like this one down there, that's going to end up being a negative 1. This oxygen, starting from 6 and counting down, 5, 4, 3, 2, 1. That's going to be a plus 1. And then a single bonded hydrogen is a 0. Oh, we missed one. The nitrogen on the right-hand structure here, starting from 5 and counting down, 4, 3, 2, 1. That has a plus 1 formal charge. Okay, so the structure on the right has only 2 atoms that have formal charges that aren't 0. The one on the left has 4 atoms that have formal charges that aren't 0, so then that would be the preferred structure. Let's do another example. Let's find the best structure for POCl3. So thinking about possible skeletons, one would be put the central phosphorus in the middle and attach everything to it. And then let's fill octets. And phosphorus already has a full octet. Now let's assign formal charges. We've seen that single bonded oxygens are negative 1. We've done this one before. Chlorine, starting from 7 and counting down, 6, 5, 4, 3, 2, 1, 0. So that's a formal charge of 0. This chlorine is a single bonded chlorine as well. That'll be 0. This will also be a 0. Here's another possible structure. If we put phosphorus attached to 2 chlorines, and then put the oxygen in the middle and then chlorine on the outside, I have a hunch that this might be a better structure, because I have already figured out from the examples before this that a double bonded oxygen has a formal charge of 0. Let's fill the octets and double check everything. So chlorine gets 3 pairs. This chlorine also gets 3 pairs. This chlorine also gets 3 pairs because it's single bonded. And this oxygen has 2, 4, 6, 8 with the whole octet. We missed phosphorus back in the left-hand structure. We didn't do that one. So starting from 5 and counting down, 4, 3, 2, 1. That's a +1 formal charge. Now let's do phosphorus over here, starting from 5 and counting down. Oh, it doesn't have a full octet. First of all, we better do that. Now let's count down from 5. 4, 3, 2, 1, 0. That gives that a formal charge of 0. We've already seen from the other example that single bonded carbons are going to have formal charges of 0. Let's look at the oxygen. Oh, we already know this one. We've seen a double bonded oxygen like this before. That has a formal charge of 0. So by rearranging this so that the oxygen was able to make a double bond instead of only a single bond, we reduce the formal charges, and that would be the preferred structure. Sometimes it's possible for multiple structures to exist that have all the same formal charges, and they only differ by the position of one electron pair. When that is the case, the actual structure turns out to be not any of them, but a hybrid of all of them. An example of this would be NO3 1-. If we draw the structure for NO3 1-, a good skeleton would look like this. Fill the octets. We're going to need 6 electrons on each oxygen in 3 pairs, and we're going to need 1 pair on the nitrogen. The electron count should be 5 plus 18 plus 1, which is 24 electrons. This structure has 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, which is too many. So what we're going to want to do is remove an electron pair from one of the oxygens and from the nitrogen and put another bond in there, and that'll reduce our count. So that's one possible structure. But we could have chosen to make the left-hand atom be the one that got the double bond. That structure would look like this. And we also could have chosen to make the right-hand oxygen be the one that gets the double bond. And that structure would look like this. Formal charges are going to be the same. We have a double bonded oxygen, which is a 0, a single bonded oxygen, which is a -1, and another one, which is a -1. And the nitrogen is going to be, starting from 5, 4, 3, 2, 1. That's going to be a +1. This nitrogen is going to be the same, +1. And then we're going to have a -1 here, a -1 here, and a 0 here. We're going to have a -1 here, a +1 on the nitrogen, a 0 here, and a -1 here. Formal charges doesn't make any difference between the 3 of them. So in fact, none of them is actually preferred. And what we have instead, I should put brackets around these because they're an ion. What we have instead is this structure is alternating back and forth between these 3 structures. So that double bond is switching between central, the left hand, and the right hand. And in fact, that extra electron pair that makes the double bond, it turns out that it's actually sort of making a 1 1/3 bond in all 3 places at the same time. That's the phenomenon that's called resonance, because it's resonating between multiple structures. Another example of resonance you can see in this compound called benzene. This is a 6-membered carbon ring. So there's a hydrogen attached to each carbon in this ring. And it alternates between double bonds and single bonds, like this. So each carbon's making 4 bonds. That's a formal charge of 0. Each hydrogen is making a single bond. That's a formal charge of 0. Formal charges are 0. But it would also have been possible for me to draw this in such a way that the double bonds were on the other 3 bonds. So double bond here, double bond here, double bond here, instead of in the 3 bonds that I drew in the left-hand structure. The hydrogens are still there, of course. Formal charges, there's nothing different about them. But what's happening is that extra 3 pairs of electrons that's making the double bonds, that's actually switching back and forth between the 2 positions. And so these 2 are said to exhibit resonance. And that means that it's not really either of these structures, but in fact, each one of these double bond, single bonds, they're not a double bond or a single bond, they're like a 1.5 bond all the time. The advantage to a species that exhibits resonance is that it's more stable than if it didn't. Because if you were going to break up this structure, it would be broken at that single bond because that's the weak point. It would not be broken at the double bond. However, if each of these bonds is like a 1.5 bond, well, 1.5 is stronger than a single, and since nothing would be smaller than a 1.5 because of resonance, that ring would be less likely to ever get broken up.